Welcome to the deep dive. I want you to just think about the last time you watched a helium balloon slip out of a kid's hand.
Oh, right. It just floats away into the sky and you just watch it go.
Exactly. And if you watch it long enough, you know what inevitably happens. It pops.
Yeah. Or maybe you've walked past an industrial site and noticed those massive, heavy-duty pressure relief valves on oxygen tanks.
Right, just waiting to vent. And, these aren't random events. They are governed by some of the most elegant, invisible physical mechanics in the universe.
And those mechanics are, well, they're operating around you and inside you every single second of the day.
It's wild to think about.
It really is. I mean, we rarely stop to think about the rules governing the air we breathe because, it's invisible. But once you understand the framework, you start seeing the matrix everywhere.
Which is exactly our mission today. We are pulling back the curtain on that invisible world. And our guide for this is actually a really highly specialized training module.
From AEIT and SAIT, right? The Northern and Southern Alberta Institutes of Technology.
That's the one. It's their instructional physics module on the laws of perfect gases.
Which sounds super intimidating.
Yeah, a little bit. It was engineered specifically for instrument technicians, the folks who deal with industrial processes, analyzer calibration, and custody transfer.
So it's an intensely specialized document designed for people who manage pipelines and refineries.
Right.
But the underlying physics they have to master to do their jobs are the exact same principles that explain why your car tires look a little flat on a freezing cold morning.
So let's unpack the core concept before we start throwing any equations around. Because to understand how gas behaves under industrial pressure, we really have to look at extreme compressibility.
Yeah, compressibility is the key to all of this.
We all know gases are mostly empty space compared to solids or liquids, but the sheer scale of that empty space is what makes all these laws possible.
It's massive.
Think about grabbing a handful of a bone-dry kitchen sponge in one hand and a handful of pool water in the other.
Okay, I can picture that.
If you clench both fists with all your strength, the dry sponge crushes down to a tiny fraction of its size. Almost nothing.
Because you're mostly just squeezing out empty space.
Exactly. But the
Yeah.
water, you can't compress it. The liquid just shoots right out between your fingers.
Right, because the physical architecture of a gas is fundamentally similar to that sponge, just on a molecular level.
The NAIT and SIST module uses water vapor to illustrate this, right?
Yeah, they do. They point out that the actual physical volume of the individual molecules in a gas is it's entirely negligible compared to the total space they are bouncing around in.
Wow.
They are widely spaced, darting around and colliding with each other like incredibly tiny, perfectly elastic billiard balls.
Millions of tiny billiard balls flying through an absolute void. And because there is so much empty void between them, when you apply force, they have nowhere to go but closer together.
Which brings us to Robert Boyle.
Yes, the 17th century chemist and physicist. The module highlights a classic, almost painfully simple experiment he performed.
Oh, the mercury tube experiment.
Yeah. He took a glass tube, sealed at one end, and just poured liquid mercury into it to trap a pocket of ordinary air at the bottom.
And you have to remember, mercury is incredibly dense. It's heavy.
Right.
So by pouring more and more of that liquid metal into the open end of the tube, Boyle was steadily increasing the physical weight, the pressure bearing down on that trapped bubble of air.
And as that mercury pressure increased, he watched the volume of the trapped air shrink. The harder you squeeze it, the less physical space it occupies.
It's a strict inverse relationship, assuming you don't change the temperature or let any gas leak out, of course.
So if you squeeze it twice as hard, it takes up half the space.
Exactly. That is Boyle's law.
The module gives a fantastic, relatable example of this in reverse. Let's go back to that balloon we talked about.
Yeah.
So you have a sealed balloon sitting on the ground, and it holds exactly 1 cubic foot of gas.
Down here at sea level.
Right. Down here, standard atmospheric pressures pushing against the outside of that balloon at 14.7 pounds per square inch absolute, or CGA.
Then you let the balloon go. As it rises higher into the atmosphere, the air gets thinner.
Right. The external pressure pushing against the rubber drops.
Let's say it drops to 10.7 psi.
Because that external squeeze is relaxing, the gas inside the balloon pushes outward. It expands.
Yeah, that original 1 cubic foot of gas swells up to about 1.37 cubic feet.
But, okay, here is where I hit a wall with the math. And I have to challenge this concept of absolute pressure.
Okay, let's hear it.
Because if I go out to my driveway and check my car tire, the gauge doesn't say 14.7 when it's flat. It reads 0.
Right, right.
So why can't we just use the numbers on a standard pressure gauge
Yeah.
to calculate Boyle's law? Like, why the absolute pressure?
That is a crucial distinction, and it trips up a lot of people. Consider your physical location right now.
Okay.
You are standing at the bottom of an ocean of air that's hundreds of miles deep.
Wow, okay.
That atmosphere possesses massive weight, and gravity is pulling it down, pressing it against you, the balloon, and your car tires constantly.
So that's the 14.7 pounds of pressure just sitting on us at all times.
Precisely. A standard gauge, the one sitting in your glove box, is mechanically calibrated to ignore that atmospheric weight.
Oh, I see.
Yeah, it is engineered to read 0 when it is exposed to normal atmospheric pressure. But Boyle's equation, where pressure 1 times volume 1 equals pressure 2 times volume 2, relies entirely on proportional ratios.
Oh, wait, I see it now. If the equation is a ratio comparing condition A to condition B,
Right.
and I plug in a gauge pressure of 0 for a tire sitting in my driveway, I'm mathematically claiming there is literally 0 force acting on the gas.
Which would completely shatter the ratio. Anything multiplied by 0 is 0.
Right.
To mathematically model reality, you have to account for the total absolute force acting on the gas, including the invisible ocean of air sitting on top of it.
Okay, so squeezing a gas changes its volume. That's Boyle. But squeezing is only half the story. Because industrial environments aren't just high pressure, they're incredibly dynamic in terms of temperature. What happens when we introduce intense heat into this framework?
That transitions us from pressure and volume interactions to the massive disruptive impact of thermal energy.
Enter Charles's law. This law focuses on the direct relationship between volume and temperature, assuming we keep the pressure completely constant.
The training module uses a great visual for this, a piston inside a metal cylinder.
Yeah, imagine a heavy, frictionless metal piston resting directly on top of a trapped pocket of gas.
Because the piston's weight never changes, it provides a constant, steady downward pressure on the gas below it.
So we have the cylinder. It's holding exactly 1 cubic meter of gas, and let's say it's sitting in a freezing environment, right at 0 degrees Celsius.
Okay, pretty cold.
Now we take a massive torch and heat that gas up to 120 degrees Celsius.
Well, that thermal energy transfers directly into the gas molecules. Heat is simply kinetic energy.
So those tiny billiard balls absorb that energy and start moving frantically.
Exactly. Because they are moving at much higher velocities, they strike each other and the walls with more force, pushing themselves further and further apart.
They literally demand more physical room to exist. They push against the bottom of that heavy metal piston and physically hoist it upwards.
Just from the introduction of heat?
Yeah. That 1 cubic meter of gas expands to 1.44 cubic meters.
That is Charles's law in action. Heat it up, and if the pressure remains constant, it will expand proportionately.
But what if the gas is trapped? What if it's sitting in a completely rigid container, like a thick steel oxygen cylinder used for welding?
Well, it physically cannot expand.
Right.
So then we are observing Gay-Lussac's law. This describes the direct relationship between temperature and pressure when the volume is strictly locked.
Let's say someone leaves that sealed oxygen cylinder out in the blazing afternoon sun. The steel heats up.
And the molecules inside absorb that solar energy.
Right. They start moving faster and violently hitting each other. They want to push further apart and expand just like they did under the piston.
But the rigid steel walls refuse to budge. The volume is fixed.
So instead of the space getting bigger, the physical force of those frantic molecules slamming into the steel walls multiplies.
Yeah, the pressure inside that cylinder builds and builds.
And that is exactly why industrial cylinders are mandated to have pressure relief valves to safely vent that gas before the kinetic fury of those molecules exceeds the tensile strength of the steel.
It's a brilliant safety mechanism, and it's driven by pure physics.
Okay, but let's unpack something here, because the training module throws a massive curveball regarding how we actually calculate temperature.
The temperature scales, yes.
The module insists that for Charles and the Gay-Lussac's equations, you cannot use Celsius or Fahrenheit. But Celsius is what the entire scientific world uses. Why throw it out?
It goes back to the underlying math of direct proportionality. These physical laws dictate that volume or pressure changes in direct proportion to the temperature.
Right.
The mathematical structure relies on multiplication and division.
Okay, I follow the math.
So consider the Celsius scale. Water freezes at 0 degrees Celsius.
Right.
If you plug a 0 into an equation based on direct proportionality, the resulting calculation will dictate that the gas has 0 volume or exerts 0 pressure.
Oh, which means the gas just, like, mathematically pops out of existence.
Right, exactly.
That is obviously physically impossible.
Yeah.
The gas is still there, hitting the walls, taking up space, even if the thermometer says 0.
The problem is that Celsius and Fahrenheit are relative arbitrary scales. They are based on the freezing and boiling points of water.
Okay.
To make these equations actually mirror the physical reality of molecules moving in space, the temperature scale must be anchored to the absolute lowest energy state possible.
Which brings into Kelvin and Rankine scales.
Yes. 0 Kelvin, which translates to negative 273.15 degrees Celsius, is absolute zero.
That's incomprehensibly cold.
It represents the complete and total absence of heat energy in the universe. At absolute zero, all molecular motion entirely ceases. The billiard balls stop dead. By anchoring the mathematical scale to that physical stopping point, a temperature of 0 actually aligns with a theoretical kinetic energy of 0, and the proportional math in these laws functions flawlessly.
It's fascinating how the math forces you to confront the physical limits of the universe.
It really is.
So we've isolated all the variables now. We know how squeezing changes volume with Boyle. We know how heat expands volume with Charles. And we know how heat spikes pressure with Gay-Lussac.
Right.
But for an instrument technician working at a massive refinery, these things don't happen neatly one at a time. The temperature's dropping while a pump is forcing more gas into a shrinking pipe. Everything changes simultaneously.
Which demands a master framework. We need a way to synthesize all these isolated physical laws into a single unified equation.
And to do that, we need the final piece of the puzzle. A way to account for the sheer amount of gas we are dealing with.
Avogadro's law.
Yes. It connects the volume of the gas to the actual number of molecules present. But the module points out that counting individual molecules is functionally impossible, so chemists use moles.
1 kilomole of gas contains a staggeringly massive number of molecules, specifically 6.022 times 10 to the 26th power molecules.
That number is almost beyond human comprehension. It's more than the number of grains of sand on Earth.
It really is hard to wrap your head around.
But when you take Avogadro's method of counting molecules and merge it with the discoveries of Boyle, Charles, and Gay-Lussac, you unlock the ultimate master equation, the ideal gas law. PV equals nRT.
Pressure times volume equals the number of moles times the universal gas constant times temperature.
And that universal gas constant, R, is the linchpin. The module lists it as 8 to 314.51 joules per kilomole Kelvin.
That specific number is what ties all these wildly different proportional relationships together into a perfect mathematical harmony.
It's basically the magic number.
Yeah, it allows us to predict complex, multivariable changes with absolute precision.
The Nayite and Sayite module gives this incredibly dense industrial example, but it's brilliant. Imagine a massive sealed industrial tank.
Okay.
It has a volume of 45 cubic meters. It's sitting at normal atmospheric pressure, about 100 kilopascals absolute, and a comfortable ambient temperature of 20 degrees Celsius.
So a completely stable system.
Perfectly stable. But then an external pump forcefully injects 40 cubic meters of liquid water into that sealed tank.
Ooh, well, the liquid water is incompressible, so it fiercely displaces the air.
Right.
The gas that previously had 45 cubic meters to roam is suddenly violently shoved into just 5 cubic meters of empty space at the very top of the tank.
And while this aggressive compression is happening, the whole tank cools down to 15 degrees Celsius.
Okay.
When I read this, I immediately visualized being trapped in a sea cave. Imagine you're deep in a cavern and the tide rushes in, sealing the only exit.
That sounds terrifying.
Right. As the incompressible water level rapidly rises, the air trapped in the ceiling has absolutely nowhere to go. The cave walls are freezing cold, dropping the temperature.
Yeah.
But because that pocket of air is shrinking so drastically as the water rises, the pressure against your eardrums would be absolutely skyrocketing.
That is a terrifying but incredibly accurate mental model. And because of the ideal gas law, technicians don't have to guess what the pressure in that tank or your cave will be.
They can just calculate it.
Down to the decimal point. Factoring in the drastic reduction in volume and the slight drop in temperature, the absolute pressure of that trapped air rockets to 885 kilopascals absolute.
That's roughly 790 kilopascals on a standard gauge. It's an immense, dangerous amount of pressure born entirely from water stealing the gas's volume.
The predictive power of that PV equals nRT equation is unparalleled for standard conditions. If a technician knows any 3 of those variables, say pressure, volume, and temperature, they can flawlessly predict the fourth.
Wow.
This is actually the cornerstone of custody transfer in the oil and gas industry.
Custody transfer, that's the buying and selling of massive quantities of gas between companies, right?
Exactly. When millions of dollars are changing hands, you aren't paying for the size of the container. You are paying for the exact number of combustible molecules inside it.
Oh, that makes sense.
Because gases expand and contract based on the weather. I mean, a pipeline in the summer heat holds a different volume of gas than that same pipeline in the dead of winter.
Right, because of Charles's law.
Exactly. So companies use the ideal gas law to standardize the measurement. They calculate exactly how much product is moving, entirely independent of the ambient temperature or pressure on that specific day.
So we have this perfect, elegant equation. We've mathematically mastered the physical universe. We can predict exactly how many molecules are in a pipeline.
Yes.
But just as you feel like a physics prodigy, the training manual pivots hard and drops a reality check.
It really does. It reveals the fundamental catch to everything we've just discussed.
The ideal gas we've been talking about.
Yeah.
The one that beautifully obeys PV equals nRT.
Yeah.
It is actually a mathematical myth.
It is. It is a simplified theoretical framework.
I couldn't believe it.
Well, the ideal model relies heavily on two massive assumptions. First, it assumes that when gas molecules collide, they bounce off each other perfectly with no energy lost and no attraction to one another.
Right.
Second, it assumes the molecules themselves are essentially mathematical points that take up absolute zero physical space.
Which, under normal, everyday conditions, relatively low pressure, relatively high temperature, those assumptions are close enough to reality.
True. The molecules are moving fast and have plenty of room, so the math works flawlessly.
But here's where it gets really interesting.
Yeah.
What happens when things get extreme?
Hmm.
You're telling me this elegant master equation we just spent all this time building is actually wrong when we push it to the limit.
Yeah, when you subject a gas to intense industrial conditions, like pressures exceeding 5 atmospheres, or plunging it into extreme cold, that ideal model physically breaks down.
Because the molecules are getting incredibly crowded.
They are forced so close together that they are no longer just tiny billiard balls flying freely through a vast void. As the distance between them shrinks, they begin to experience attractive intermolecular interactions.
Wait, I think I see where this is going. If you squish them together hard enough, they start pulling on each other.
Yes.
They get slightly sticky. And if they're sticking together, they aren't flying around as independently, which means they aren't hitting the walls of the container with the same amount of force. The pressure drops.
That is the exact mechanism. The actual pressure of a real physical gas under extreme compression is lower than what the ideal gas law predicts.
Oh, wow.
Furthermore, because you've squeezed out so much of the empty void, the physical space the molecules themselves occupy is now a significant fraction of the total volume. You can no longer pretend their size is zero.
So how on earth do the industrial technicians fix the math? I mean, they are dealing with extreme pressures every day. They can't just throw their hands up and guess when millions of dollars are on the line.
They adapt the framework by introducing a new variable called Z, the compressibility factor.
So PV equals nRT becomes PV equals Z nRT.
Exactly. The Z factor acts as a necessary correction. For an ideal gas at low pressure, Z simply equals 1.0. It multiplies by 1, changing nothing.
Makes sense.
But for a real gas behaving badly at high pressure, Z drops below 1.0.
Let's apply this to that custody transfer idea.
Yeah.
If you are a massive energy company buying thousands of cubic meters of highly compressed natural gas, and you rely strictly on the ideal gas equation without that Z correction factor, your calculations are going to be artificially inflated.
Absolutely.
You'd be calculating volume and pressure as if those molecules were still bouncing perfectly and taking up zero space.
Which means you would be paying millions of dollars for gas that simply isn't there solely because you failed to account for the physical reality of molecules crowding and interacting.
It is genuinely incredible how this technical manual takes you on such a complete intellectual journey.
It really covers a lot of ground.
We started with Robert Boyle in the 1600s, pouring mercury into a tube to prove that gases are mostly vast, empty spaces that shrink under pressure.
Then we injected the furious kinetic energy of heat with Charles and Gay-Lussac.
Right. Confronting the reality that our math only works if we anchor it to absolute zero, the complete cessation of atomic movement.
And we tied all those threads together with Avogadro into this beautiful, sweeping master equation that can perfectly predict the chaotic environment of a flooded industrial tank.
Only to finally hit the wall of reality. Molecules aren't perfect mathematical points.
No, they are not.
They take up space, they get crowded, they attract each other, and they force us to bend the math to match the messy reality of nature.
Because science is a constant process of building a model, testing its limits, and refining it when reality refuses to cooperate.
And understanding that process completely changes how you interact with the world.
It really does.
The next time you see a party balloon expanding as it floats away, or you hear the hiss of a pressurized aerosol can, or you press a gauge onto your car tire on a cold morning, you aren't just looking at mundane, everyday objects.
You're seeing the physics in action?
You are witnessing the invisible, powerful, mathematical laws of the universe playing out right in front of you.
Absolutely.
But wrapping up this deep dive leaves me with one final provocative thought. Something the module flirts with, but leaves hanging.
Oh, what's that?
Well, we know that if you pump a gas past 5 atmospheres, the molecules crowd together, they start sticking, and they stop acting ideally. But what happens if you just, keep going?
Keep increasing the pressure.
Yeah. If you keep increasing the pressure more and more and more,
Mm.
if gas laws are entirely predicated on the vast empty space between molecules,
Mm.
does a gas eventually stop being a gas altogether if you squeeze all the empty space out of it?
That is a very interesting question to leave off on.
Something to think about. Until next time, keep diving deep.